Hey guys, and welcome back. So in this video, this is the sixth problem for the first recitation for signals, and we're going to do a different type of problem than the first five. And well, really we're not. We're just taking the first five problems, but we're reversing what we did. We're taking a number that's in polar form, converting it back into rectangular form. So this is our number that we're going to use. We're going to use 3 times e to the minus j pi over 8. This is going to be our the number that we use. This is a complex number that's in polar form, and our task is to turn this or to convert this back into rectangular form. So back into something like we saw the original problem as in the first five problems. So if you want to pause the video, now's a great time. And I guess now I'm just going to continue with solving the problem. So one of the things, and it's actually a mistake I realized that I made in the first video that I made, I said that we were going to be using Euler's identity. What we're actually going to be using, what this is called, is Euler's formula. Euler's formula says that e to the j theta is equal to the cosine of theta plus j times the sine of theta. This is Euler's formula. I had said it was Euler's identity. Euler's identity actually comes from Euler's formula. Pretty much what Euler's identity is that if I take e to the j pi, so if I made theta equal to pi instead of being equal to something that can vary. So theta here can be, just some angle that we put into that we use to determine the phase angle of our complex number. If I just set that to be pi, e to the j times pi, that's going to be equal to the cosine of pi plus j times the sine of pi. And so hopefully you remember your trig a little bit, and I'm right now moving my left arm to kind of, or maybe I should just go ahead and draw my axes. So if I have my cosine is pretty much, if my angle is rotating around like this, my cosine is going to be my x value, my y value is going to be my sine. If I rotate through to pi, pi would bring me over to here, right? I would rotate through that angle would be pi, right? If I rotated all the way around, that would be 2 pi. So if I rotate through pi here, what's the sine of pi? Well, if I rotate all the way through, I'm over here on my, I guess we could say my negative x-axis or my negative real axis. I've got no y component, or I've got no imaginary component here. So, and also, hopefully you just remember that the sine of pi is 0. So my sine of pi here is 0. I'll have no imaginary component in this number. This number is going to be purely real. It's going to be purely the cosine of pi, which is -1. So that's pretty interesting, right? It's cosine. So if I take e to the j pi, that's going to be equal to -1, or what this is sometimes written as is e to the j pi plus 1 is equal to 0. That's Euler's identity, and it is a pretty powerful identity. Anyway, that's kind of an aside, but actually we're going to be doing stuff like this for this next bunch of problems. So, like we did in the first video, the only thing I'm going to do to this equation, to have it kind of like fit our needs, is to say like this e to the j theta looks a lot like this part of the problem, but we just have to multiply it by, let me choose a good color, we just have to multiply it by a magnitude. We have a magnitude of 3 here. So if I multiply this e to the j theta times m for magnitude, then I would just multiply both my cosine and my sine by that same m. And now I've got a really clean way of figuring out what my rectangular form for these complex numbers is going to be. So anyway, well, I guess at this point we can pretty much just get out the calculator. Or I shouldn't say we can just get out the calculator right now. Let's actually just go ahead and write this all out before we get out the calculator. So 3e to the minus j pi over 8. And even let me rewrite this. Instead of minus j pi over 8, I'm going to write that as e raised to the j negative pi over 8. So our theta in this example is negative pi over 8. Because keep in mind here, theta is positive. We have a positive theta here. So if I have a negative number here, I want to factor that negative sign into my theta. That negative sign is part of the theta. It's not part of the j here. So that is going to be equal to, if I have 3e to the j minus pi over 8, that's going to be equal to, my magnitude is 3 times the cosine of that theta. My theta is minus pi over 8. And now I add that to my magnitude, which is still 3. 3 times j times the sine of my theta, times the sine of minus pi over 8. And now, this is the point where we can actually, I guess, get out the calculator and maybe chug through this. So now, let me get the calculator. Clear. And I'm going to take pi divide by 8 equals, now I take the minus of that and the cosine of that times 3. So I get 2.7716 is equal to 2.7716 plus, so now clear that. Let's see, pi over 8 minus, and now I take the sine of that, multiply it by 3, and I get minus 1.1481. Minus, so instead of a plus here, I'm going to put a minus 1.1481j. That's what that number was, right? Minus 1.1481. Yeah, that's it. So that's pretty much it. Excuse me, sorry. That's pretty much it. We took our original polar form of the complex number, and now we have it in rectangular form. And that's pretty much our final answer. And that's basically how you would do this conversion. One last thing before I leave you. One of the things that we're going to use this formula a lot in signals. It's going to come up almost all the time. And we really don't get a chance to ever go into any type of detail or any type of depth as to where this comes from. And it is a very interesting derivation. So I wanted to just point you towards where you can find that. So as you probably can figure out by how I do these videos, I'm a huge Khan Academy nut. So I'm on the Khan Academy main page here. It's just khanacademy.org. If I go up to watch, go up to math, over to calculus, and it takes me to calculus. And now I'm going to go down to integral calculus, and I scroll down. It might, depending on when you access this, this might have changed. They change around how they lay this stuff out from time to time. If you watch, first off, here is the kind of the crux of what we're doing. This video that they have right here is called Euler's Formula and Euler's Identity, where they actually arrive at Euler's Formula and Euler's Identity. However, if you want to get the complete story, the complete total story of where Euler's Formula comes from, start with Maclaurin and Taylor's series Intuition. If you start at this video, work down to that video, so that's 1, 2, 3, 4. That's 5 videos. If you watch those 5 videos, you'll have a very good understanding of where this formula comes from. And it is, you know, really interesting stuff. It's stuff that it's definitely worth watching. So it's worth watching even if you're not in this class or beyond this class. It is a very interesting video. It's one of the most kind of profound formulas in mathematics. So anyway, thanks for watching, and I guess I'll see you in a future video. See you soon.